In the 7th lecture on statistical methods in high-energy physics, let's open a topic of the interval estimation. Everybody knows that an outcome of a measurement is quoted as "we harvested 10 tons of potatoes plus minus 500 kilograms." This plus minus denotes an interval. In this video, you will learn what this interval usually means. You might ask, why should we bother with some general interval estimation after all the effort we invested into finding estimators of the mean value of any probability density function together with its variance? Well, the answer is simply, variance is, indeed, a square of the standard deviation, but we haven't assigned any meaning to the standard deviation up to now, apart from saying that a higher standard deviation means a wider probability density function. We really need to sit down and think about the basics of construction of these intervals, which we quote as a statistical uncertainty of our measurements. Let's start with the frequentist framework first. Never forget that within this framework, the true value of a parameter of interest is not a random variable. It is a fixed number. While this is quite natural, it has some unintuitive implications on the meaning of the interval corresponding to our measurement. Also recall that the frequentist approach assumes that you can repeat one experiment infinite number of times under identical conditions. Statistics uses the keyword confidence interval, but don't get confused by it. You can have complete confidence in the frequentist framework to never work with anything like confidence, feelings, or subjective views. In the frequentist approach, boundaries of the confidence interval are random variables, and therefore their numerical values differ from one repetition of an experiment to another. If you build your confidence interval in each repetition of the experiment, then the interval will contain the true value of your parameter in n% of cases. The number n is called a confidence level, shortly CL, and we say we are constructing a confidence interval at a confidence level. Let's stress again one very important thing. The confidence interval is sliding. It is different from one experiment repetition to another, while the true value of the parameter of interest is fixed. To make this crystal clear, people say that the confidence interval covers the true value of the parameter in n% of the experiment repetitions. We use the word cover to stress that it is the interval that is variable, and sometimes does, while sometimes does not cover the fixed value of the true parameter. For certain good reasons, people often choose the confidence level to be 68.3%. However, many other values are also quite common. Just keep in mind that the confidence level is a predefined number that must be chosen before you do your experiment. For the frequentist interval estimation, we will show a classical construction that was developed by Neyman. As a first step, we construct a so-called confidence belt. Let's draw a plane with the true value of our parameter on the x-axis and the estimated or observed value on the y-axis. We know that the true value theta is fixed, but we can construct a probability density function for our estimate theta hat for any value of theta. Recall that theta hat is a random variable. This PDF is often assumed Gaussian, but it can also be a Poisson, binomial, or any other distribution, depending on our measurement. Let's just call it f of theta hat with parameter theta, and let's draw a couple of these functions into our graph. It would be great to have a third axis available to draw the probability density functions, but since I only have two, I will draw these functions into the plane. For each of these probability density functions, we can take an interval for which the integral is equal to our chosen confidence level, say 68.3%. Obviously, this interval definition is ambiguous, but we will describe the most common choices later. By connecting endpoints of these intervals, we get the confidence belt. An important property of the belt is that theta hat falls into it with a probability equal to the confidence level, regardless of the true value of theta. If the experiment is reasonable, then the boundaries of the confidence belt should be monotonic functions of theta hat. It would be weird if they were not. The estimated theta hat would be really useless if it predicted, say, high values given both low and high values of true parameter. So obviously, the higher the value of theta, the higher the quantiles of the probability density function for its estimator should be. All this to say that there is a one-to-one mapping of the confidence belt boundaries to the true parameter values. Let's now consider some concrete value of theta and an outcome of a measurement theta hat ops. A straight line and theta hat ops crosses the confidence belt at 2 points. Let's call their corresponding values on the x-axis theta 1 and theta 2. These 2 points are boundaries of the confidence interval at the chosen confidence level. Surprisingly, this is quite easy to prove. For this purpose, let's draw a line segment at theta that's inside the confidence belt. By construction, the line at theta ops crosses this line segment in 68.3% of experiments, or whether the predefined confidence level is. Whenever these two lines cross each other, the confidence interval covers the true value of theta, otherwise it doesn't cover it. Therefore, the confidence interval covers the true value of theta in a fraction of experiments equal to the confidence level. We have just examined the construction of the two-sided confidence interval. However, there is an ambiguity in how to place the intervals, or in other words, how to build the confidence belt. Let's call the upper boundary of the belt u sub alpha of theta and the lower boundary v sub beta of theta. In general, one places boundaries of the belt such that the integral of f of theta hat with parameter theta d theta hat from u sub alpha of theta to infinity equals to alpha, and the integral f of theta hat with parameter theta d theta hat from minus infinity to v sub beta of theta equals to beta. A popular choice of the values alpha and beta is a common number gamma over 2. The resulting confidence interval is called central. Very often, people choose the number gamma to be 1 minus 0.683, which results in a 68.3% confidence level. Of course, other choices of the alpha and beta are definitely possible. An important situation is when we choose either alpha or beta to be 0. In this case, we get a one-sided interval. If alpha is 0, then we get an upper limit on theta. It means that a fraction of 1 minus beta of experiments result in an interval minus infinity to theta 2, with theta 2 greater or equal to theta. Analogically, if beta is 0, then we get a lower limit on theta. In that case, a fraction 1 minus alpha of experiment result in an interval theta 1 to infinity with theta 1 less or equal to theta. Until now, we treated the probability density function for the estimator of theta in the most general way. However, don't be scared. The big moment for Mr. Gauss is here. One could write whole novels about him and his famous distribution. Actually, they already exist, but names like A Handbook of Statistics don't make them bestsellers. Anyhow, the probability density function for the estimator theta hat can be approximated by a normal distribution quite often, thanks to the central limit theorem and the fact that the estimator is often based on a sum of many random variables. For this reason, the relation between confidence intervals and the normal distribution is very well known. It will be a matter of just few minutes to show that, indeed, the interval theta hat ops plus minus the standard deviation of its probability density function covers the true value of theta in 68.3% of experiments. The number 68 is so famous that you will never meet a person who doesn't know it. Well, at least in the Czech Republic, where the legendary hockey player Jaromír Jágr, who wears 68 on his jersey, was born. Let's assume that f of theta hat with parameter theta is a normal distribution with mean equal to the true value theta and a variance sigma sub theta hat. Further, let's notice that the value alpha and beta can be expressed with the use of cumulative distribution to the standard Gaussian. We will denote the cumulative distribution G of theta hat ops with parameter theta and sigma of theta hat for a Gaussian with arbitrary parameters and phi of theta hat ops for the standard Gaussian. We can write alpha equals to 1 minus g of theta hat ops with parameter theta 1 sigma of theta hat, which equals to 1 minus phi of theta hat ops minus theta 1 over sigma of theta hat. And also beta equals to g of theta hat ops with parameters theta 2 and sigma theta hat, and that equals to phi of theta hat ops minus theta 2 over sigma of theta hat. Solving the equations for theta 1 and theta 2 gives theta 1 equals to theta ops minus sigma theta hat times inverse to phi of 1 minus alpha, and theta 2 equals theta hat ops minus sigma of theta hat times inverse to phi of beta and that equals to theta hat ops plus sigma of theta times inverse to phi 1 minus beta. If we focus on the central confidence interval for which alpha equals to beta equals to gamma half, then we choose inverse to phi of 1 minus gamma over 2 equals to 1. Then we get 1 minus gamma equals to 0.683. We've just shown that the interval theta hat ops plus minus the standard deviation of its PDF, if the PDF is Gaussian, covers the true value of the parameter theta with the famous probability of 68.3%. Unfortunately, the true value of the standard deviation is known very often. In practice, we replace it by its estimator. This approximation works very well if we have good enough data, and therefore the estimation is a good approximation of reality. Until now, We assumed that there was just one parameter of interest. However, humans are curious, and we might be interested in several parameters at a time. For the confidence regions in n dimensions, there is a generalization of the two-sided confidence interval. Let's show how it works in 2 dimensions. Imagine you are a tourist and you want to climb a hill. Before the trip, you look at a topographic map, which has all these lines, called contours, indicating points with the same elevation. The contours drawn around the hill will tell you how high and steep it is at each point. If instead your hill is a two-dimensional probability density function, then the contour will mark the points with the same probability density. The confidence region can be chosen as an area enclosed by one such contour. The corresponding confidence level is nothing but an integral of the two-dimensional probability density function over this confidence region. This approach is particularly well motivated if the two-dimensional probability density function is a normal distribution. Recall that an n-dimensional Gaussian can be written in the form g of theta vector hat with parameter theta vector equals to 1 over 2 pi times determinant of v to the power of n over 2 times exponential of minus 1/2 times q of theta vector hat and theta, where q of theta vector hat theta equals to theta vector hat minus theta vector transposed time inverse to v times theta vector hat minus theta vector. Obviously, contours of a two-dimensional Gaussians are lines along which the quantity q is constant. A confidence region constructed as an area enclosed in a contour is a natural generalization of the two-sided central intervals that we've discussed for one-dimensional probability density functions. Given that q is distributed according to the chi-square distribution with 2 degrees of freedom, as we stressed in one of our previous lectures, it is fairly easy to calculate the confidence level corresponding to some fixed value of q gamma. 1 minus gamma equals to integral of 0 to q gamma of f of chi squared with 2 degrees of freedom d chi squared, and therefore q gamma equals to the inverse to capital F of 1 minus gamma with 2 degrees of freedom. Tourists in n dimensions have tougher life because it's not easy to climb in hyperspace. Fortunately, everything else stays the same, so we can just use the chi-square distribution with n degrees of freedom. If we choose the confidence interval and want to calculate the corresponding quantile of the chi-square distribution, then we just need to inverse its cumulative distribution. We get q sub gamma equals to inverse to the capital F of 1 minus gamma with n degrees of freedom. It's important to note that because the covariance matrix is positive definitive, in 2 dimensions, points with constant q will form ellipses. In higher dimensions, they will form ellipsoids or hyperellipsoids. If you do not see it immediately, you just need to recall your old lectures on linear algebra, or you can just take it as a fact. You will see this a lot when we talk about the method of maximum likelihood. Another interesting thing to note is that q gamma is different for a fixed confidence level but different number of dimensions. Check value of q gamma for different dimensions and 2 commonly used values of the confidence level. You do not need to memorize this table, because you can always look it up in any statistics book or on the web. However, note how the value of Q gamma grows with the number of dimensions. It means that in higher dimensions, your confidence region must cover geometrically larger area to have the same probability of covering the true value of the parameter. We will come back to this again when we talk about the method of maximum likelihood. Let's close the chapter on confidence intervals by a short remark on the Bayesian approach to their construction. In the Bayesian framework, the true value of the parameter of interest is a random variable. The posterior probability characterizes our best knowledge given data and our chosen prior probability. Recall the Bayes' theorem. F of theta given data x vector is proportional to f of x vector given theta times pi of theta. Actually, the posterior probability density function is a much more complete information than just an interval. However, for brevity, one can pick an interval in some reasonable way, and the integral of the posterior probability density over this integral gives its confidence level.